This is the small last sub-chapter of flight mechanics, wherein we are going to look at something called as body frame reference equations. As an undergraduate student, you do not find so many questions on this, particularly from objective exam point of view, because these are very mathematical subjects in nature, where you are looking at axial frame transformations. So let's understand first this entire concept, what it is about. This is my aircraft. My aircraft is now flying like this anywhere, doing something. If I am on the aircraft, there are three axis systems, right? Roll, pitch, yaw, based on which we defined. But for the person on the ground, aircraft may be in a completely different maneuver. For example, look at this. Now I am a guy standing in this corner of the room and looking at this aircraft. In my case, my axes are X, Y, Z. And I will report that this aircraft has a net velocity in this direction with X component, Y component and Z component as some meter per second. A guy in this aircraft like this, or a guy just moving parallel with this in the air, would see it has these orientations. Which means depending on the choice of frame, the reported values change drastically. So far we have been looking only at aerodynamic frame of reference, which means the frame of reference frozen with respect to aerodynamics of the aircraft. But this need not be the case. As a flight mechanics engineer, you may be asked to look at from the ground when rudders are going to pick up the signal. So the practicality is, for any frame of reference, you should be able to transform all set of equations. We have seen phugoid, Dutch roll. Some of the phugoids are so light in nature, in aerodynamic frame of reference, practically they are very difficult to detect. How are they detected? By transforming the units to ground frame of reference. Wind. If there is a strong headwind or a tailwind, what is tailwind? This increases true ground speed. Headwind decreases to ground speed. Now, range of an aircraft is dependent on this, as we have seen. So depending on the choice of frame, some of these parameters would change. So this is a very quick summary chapter in which we are going to look at these different frame of references and quickly practice them on sample simple questions. This is a small chapter because this is not very important from a theory perspective for undergraduate student. It is very mathematical in nature. So first is aerodynamic coordinates. Aerodynamic coordinates are basically on this axis, right? X, Y, right? Now in these aerodynamic coordinates, the frame of reference, you have this as positive angle of attack, right? This is X, Y, and product coming out of this, out of the plane, is Z, right? Now in this, right hand rule is used. So my frame of reference is X, Y, Z, right? Which is very apparent and simple. This frame of reference is very simple and important to understand the locations. Particularly when, rather than an aerofoil, you are looking at an aircraft, this axis of symmetry becomes your main axis, right? So the coordinate systems here would have this aircraft, wherein this would be considered positive, right? This towards the wing is Y and Z. So you have these three frame of reference. Most of our analysis so far was focusing on this coordinate frame called aerodynamic coordinates. But there is another option. Option number 2, which is body fixed coordinates. What is this? This is a coordinate system having origin at CG. Now you are looking at CG of any random shaped object. That's why it is called body fixed. Fixed with respect to center of gravity of an object. In case of aircraft, how it will be? X-axis has been taken along length of the aircraft. So this is called as XB. This is ZB, right? And x cross y is z, So YB is taken across span, right? This is body. Now what is the difference between body frame of reference and aerodynamic frame of reference? We have seen this multiple times, right? Why is this? Because of angle of attack, right? So because of the natural settings, the body axis and aerodynamics axis may vary, but they are very close to each other because both of them take an aircraft as a base, center of gravity and X, Y, Z, right? See these axis point locations, X, Y, Z, right? X, Y, Z. You have to show it like this because right hand rule should apply, right? Aerodynamics would be almost similar. Now the third is Earth based coordinate system, which means you are no longer looking at aircraft as a body, but you are looking at Earth fixed system. What is this coordinate system? You have east, west, north, south, right? Y is taken in east direction and X is taken in north direction. And S, this is the, so if this is my plane, right, out of plane component is considered as Z. So what is the reference on the ground plane? This is Y, east, this is X, down it's Z. As I keep moving up in height, my Z goes up. So height of object implies Z. Right? At what height aircraft is at? In Earth frame it is determined by Z because Z is down. How far I have gone from my starting point in east? This. And how far north is governed by Y, X, Y, Z. So these are the three frame of coordinates which an undergraduate student should be very much aware of to transform this set of equations. Then the last one is of course parallel is atmospheric coordinates. What are these coordinates? They are coordinates in Earth fixed but transposed with velocity, which means this is my Earth specific coordinate frame of reference, right? X, Y, Z. Now my aircraft is here. Here my distance may look something like this, right? This is the vector R. So this is my original point, say Mumbai. This may be very cumbersome to measure, right? So what I do? I transform this coordinate frame of reference into a local atmospheric frame of reference which is parallel to this but on the aircraft, right? At t equal to 0 they coincide, and then as the aircraft moves the frame itself moves with it. Now notice the difference. In such an attitude, what will be the body fixed axis? ZB. YBs will be different, ZB will be still pointing down. But what will be Earth specific axis? They will always remain like this. Because I have not transformed the directions, I have only transformed the location. So this is also called as location transformed coordinates. Are we clear about all these four types? So these are the four types of coordinate frame of reference which aerodynamists use and flight mechanics engineer should be well aware of. Armed with this understanding, now we have to look at the velocity, right? V is velocity of body, right? Velocity of wind is written as VW, right? So what is the ground speed? V plus VW vectorically, correct? This we have seen. Ground speed is always true airspeed plus wind speed. Now total airspeed is written as, this you have to see very carefully. The speeds in all three directions. You guys will get confused at this point because you are very much used to seeing this velocity, right? Or this velocity, right? Or this velocity, or climb. Imagining all the three velocities is difficult. Some maneuver like this. But you have to imagine now. In body frame of reference, that is XB, YB, ZB, ZB, XB, YB, my aircraft would have some climbing tendency in Z direction, that is V, ZB. In this orientation, it would have forward velocity, XB, and it would have a yaw velocity, a side slip, going like this, right? If aircraft has a side slip, it's crabbing like this. It has this component and this component, that is V, YB. So the net of the three velocities is airspeed of an aircraft. Now notice, the speed on the ground may be different depending on the orientation. And this is called transformation equations, right? What will be angle of attacks now in this frame? Right? And what will be the side slip beta? Because we have seen Z component and X component finally give me alpha, and X component and Y component give me finally beta, right? Because that's how the effective velocity forms an angle. So these are the two angle of attacks. One is angle of attack and one is side slip angle, which is in this frame of reference. From this I could actually do beta equivalent, that is experimental side slip, as sine inverse of Vyb upon root of Vxb square plus Vyb square plus Vzb square. Because in experiment you would have this net velocity being measured from where? Delta P, Pittot's tube or any other delta P sensing measure. Vyb is measured through sensing, right? Maybe pressure or accelerometer. So you would get this value, and when beta is equal to beta A, you have alpha approximately 0. So if there is no angle of attack, experimental value will match with this. Are we clear? Now, for a small increase in angle of attack, this equation does not hold very true, right? So what do you have to do? Vxb is root of V square minus Vyb square minus Vzb square. I have just used that original equation, all three component summation. Now Vzb I substitute as Vxb tan alpha, and this as Vxb tan beta, right? So from here I obtained Vxb equal to root of V square minus Vxb square sin square beta upon cos square beta plus sin square alpha upon cos square alpha, right? Which is basically the tan squares alpha. This I can further simplify to say V cos alpha cos beta upon root of 1 minus sin square alpha sin square beta. I have just used tan relations, tan A tan B relations. So Vxb, when there are all the three components of velocity, that is angle of attack and side slip present, is given by this. Similarly, what is Vyb? It is V cosine alpha sin beta. Now rather than cosine you have sin beta upon denominator remains same. What is Vzb? V sin alpha cosine beta upon this magnitude. So only the interchange of sine and cos in the numerators of alpha and beta respectively give you the resultant velocity. So you have transformed body axis and angle of attack to give you unique relations. Now, if you are clear with this aspect, right, let us look at one question wherein a rocket with 1 kilometer per second velocity, okay, this is effective velocity, has angle of attack 30 degree and side slip of 20 degree. How would you solve this? You would simply put Vxb as V cos alpha cos beta upon root of 1 minus sin square alpha sin square beta, right? And similarly, if you are asked what is the vertical velocity with respect to angle of attack, you would do this component sin alpha cos beta and you would get that as 476.87 meter per second. Okay? Now, in this equation, if we use experimental side slip angle, the beta E angle, how would I simplify these equations? Beta E was, what was beta? Experimental sine of yb upon, sine inverse of yb upon root of xb square plus yb square plus zb square. If I invoke that definition, I would have Vxb as simply V cos alpha cosine beta experiment. This entire denominator goes away because that is the substitution. Similarly, what is V by beta? Sin beta E. And what is Vzb? V sin alpha cos beta E. These are approximation equations which are typically used to denote the speed and the velocity when experimental values are closer to theoretical values. And when does that happen? Small angle of attacks. So these are always true equations based on pure mathematical transformation. These are approximate true based on experiment and transformation. In the same rocket question of 1000 meter per second and alpha equal to 20, 30, beta equal to 20, if you would put this, okay, what would be the components? Now you would have Vzb 469.85 meter per second. Compare this with 476. How much is the error? Less than 1% or about 1%, which is acceptable, right? But see how easy these equations are used. They are very easy. Sine, cosines, simple signs. And Vyb would be around 342. There you were getting 348. So xb is always underestimated, the forward velocity. Other out of plane components are overestimated with this. So this underestimates this and overestimates forward component, which is fine, right? You will estimate slightly more lift and drag, which you can correct. So this is the objective, right? Now, armed with this now, what you have to think about is an airplane model is mounted in a wind tunnel. Now, this transformations that you have seen have an implication of the stability equation, and we will understand this through one example. An aircraft model mounted in a wind tunnel with alpha set at 12 degrees. Okay, so this is my aircraft mounted in a wind tunnel, right? This is the mounting and these are the sensors, right? And side slip angle beta is estimated to be 0.25. Find beta alpha, that is actual angle, and estimate the change in your normal movement coefficients with respect to beta alpha. Now, why does this happen? Because in estimation, you have tan beta E, right? The projection components, alpha, and here you had this beta. The projection of A over B and then B over C gives you theoretical value of things. So you would have actually tan beta alpha into cos alpha. So V cos alpha is the major component of V. Tan of that is what experiment is able to measure, right? We have seen that derivation. If this is my aircraft in this attitude, the final double projection on the ground with this projection is what I am able to measure as realistic beta, right? But actual beta is different than that. It is this divided, it's angle made by this in the three-dimensional plane. It's a solid angle. But what I am measuring is projection angle. You see this difference? If I am asked to measure angle between these two vectors, how would I do? I would first transform this in this plane. Then I would transform the component and in this plane. You see this? This is the loss of equivalence because in experiment you are measuring this. So experimental value is always lower than actual value, and moment is alpha tends to 0, they start matching, because moment alpha is 0, you are actually coming in one plane. So mathematically you have to understand that out of plane solid angle measurements always go through two plane projection routes, because of which this error arises. So now we know this something very important. So what does that mean? Tan of beta alpha would be tan beta E upon cos alpha, and so beta alpha, the actual angle would be tan inverse of tan beta E upon cos alpha. Now you substitute. Alpha is not very small, right? 12 degrees is not that small. You would get this to be 8.2 degree. See the difference. Now what is del C by del beta? It is cos alpha upon cos square beta alpha plus cos square alpha sin square beta alpha delta beta E. Where does this relation come from? This relation C comes from yawing moment equation. Now if you substitute, you would have this answer as 0.245. This is the change in yawing moment because of this underestimation of beta alpha. So you have to account for this. Experiment will give you this, but this will give you this. This small delta is producing this much yawing moment difference. So you have to be very careful about this, and that's where the role of this transformation comes. A flight mechanics engineer should be well aware of these so that he knows what approximations I have done. Right? Next question is almost the similar. Aircraft model is mounted in a wind tunnel with an angle of attack at 40 degree. Now see, at this higher angle of attacks, your divergence will be even higher. And experimental side slip is 30 degrees. See how the angles are involved. Now I can immediately say tan beta alpha is tan beta E upon cosine of alpha. Right? And if I do this, if you substitute these two numbers, beta alpha would be 37. 7 degree difference in projection versus actual. Now I know del C by del beta alpha. What is that? Cos of alpha upon cos square beta alpha plus cos square alpha sin square beta alpha del C by del beta E. Right? Here we have been given del C by del beta E, the yawing moment, as 0.25. So this is what you estimated from experiment, the yawing moment with respect to side slip, right? To correct your side slip. Now this is the relation. Now if you substitute here, you would get 0.225. What is the delta? 0.250 minus 0.225 upon 0.250. This is the delta error with respect to experiment. This is what? 0.025. So this is about 10%, which is not a small number. 10% error needs to be corrected, otherwise your aircraft will start drifting like anything. Which means these transformations of axis, this plane to this plane, has costed you 10% error. So you have to use these retransformation equations that we just saw to get back the actual value. You will be confused. As an undergraduate student, do I need to really remember these? These correction factors of the projection, for example, cos alpha upon cos square beta alpha plus cos square alpha plus sin square beta alpha, even I don't remember. You don't have to. There are tables and these formula sheets in real life are available to you. You need to know these concepts of the projection. In undergraduate examinations also, you are not asked with such a complicated yaw moment correction equations. You are asked to find a way through which these angle calculations are made. So always understand the concept. Experimental side slip and theoretical side slip vary because of this projection, and therefore yawing moment needs to be corrected based on these difference by transformation. Next question will clear some of your even more concepts. The velocity vector of an aircraft in body fixed axis is given by this. Okay, what is body fixed? From center of gravity, Z, X, Y. Angle of attack is alpha and side slip is beta. Then which of the following relation is correct? u equal to v sin beta cosine alpha, v equal to v sin beta, w equal to v cos beta sin alpha. This is option A. Option B is u is equal to v cosine beta cosine alpha, v equal to v cosine beta, w equal to v cosine beta sin alpha. Option C, u equal to v cosine beta cosine alpha, w equal to v sin beta, and w is v sin beta sin alpha. And option D is u equal to v cosine beta cosine alpha, v equal to capital, the bigger V, that is the total velocity, sin beta, w equal to v cos beta sin alpha. This is a very simple projection questions, right? In body fixed axis, when I am asked to find this out, you don't have to transform anything, right? This is my aircraft. This is my body fixed Z, Y, X. If my side slip is beta and angle of attack is alpha, this is roughly the orientation, and this is the net velocity vector. First and foremost thing I know I have to do is treat for beta, the projection, right? What would that projection be? V is v sin beta, right? Because you have u, v, w, right? I'm going to show v here, right? In this direction. So u, v producing this horizontal vector, w producing this vector. Why did I do this? Because angle of attack is always with respect to this base plane, right? Actually, in body frame, this is with respect to this base plane, how much up the vector has risen. So this component is first needs to be found out by v sin beta. Are we clear? Why is v sin beta and not cos beta? Because v cos beta would give me other directional component, right? Beta is the side slip, right? Beta is the side slip. So y-axis component is v sin beta. What is u? V cos beta into cos alpha. Again, body frame. So v sin beta will give me this direction velocity. V cos beta will give me this. But projection of this is with respect to alpha. So u would be v cos beta, which is this 1 minus root of v square, the vertical velocity square, into cosine alpha, because now this vector forms angle alpha, right? So this is u, and then therefore what is w? V cosine beta, the vector here, into sine alpha, right? This is the w now. Now let us look at options. This option is gone, right? So the correct option would be u is v cos beta cos alpha, cos beta sin alpha, v is equal to sin beta. My bad, I wrote the option wrong here. It was this. And this, by the way, was one of the gate questions. Now you see, undergraduate students are expected to know not the mathematical formula at the end, but the concept of projections and transformations. And that's my strong, sincere urge to you, that no matter what happens, please try to see that you understand these definitions quite well. Okay? So, if that is the case, let's look at one more question before we close this chapter. Right? In the definition of Eulerian angle phi, that is roll, theta equal to pitch and psi is equal to, this we know, phi, theta and psi. These are Eulerian angles. In these Eulerian angles, the correct sequence of rotations required to make inertial frame coincide with aircraft body frame is. So inertial frame to coincide with body frame is? And options are first psi about z, then theta about y, then phi about x. Then second option is theta about y, then phi about x, psi about z. Okay? C option, phi about x, theta about y, psi about z. And last option, psi about z, theta about x, phi about y. So I am just calling this about by denoting the subscript. Now, we have always seen side slip first needs to be corrected, right? Because that is the projection onto the plane, correct? Any side slip which happens with respect to this is the first correction that you have to make, right? Now, inertial frame of reference is somewhere fixed on the ground, right? Like this. I have to, now inertial frame may be in atmospheric frame, so I have just taken it like this. So my aircraft is somewhere doing this nonsense, right? Phi, theta, psi, right? If there is only psi about this, what do I need to do? This psi is corrected about z axis, because psi is about this axis, correct? Which means first I took this from inertial frame to atmospheric inertial frame. It does not require any transformation, it is linear interpolation. Then I corrected it for psi. So first sequence has to be psi about z. So either A or D, right? But if you do first theta, what is the problem? You lose this. Now you cannot change it. Yaw is the most important. Otherwise the projections would go wrong. So these two options are useless. Once you have now done about this theta is about which axis? Theta, y axis. You get this? You have corrected for this axis, right? The side slip about z. So you have this plane, you corrected it about z. By rotating about z, you got psi corrected. Now you have to correct for theta, pitch. How would you correct for pitch? About this axis. This motion is about y axis. So even this option is gone. About x axis there is no meaning. And then phi is about x axis. Roll. So the correct answer is A. Now you see, this is another gate question. None of them asked you to write down any complicated projection matrix or any mathematical derivations, because those derivations are there. The tabular transformations are in the book. As a flight mechanics engineer, you are expected to know the concept of these transformations, the yaw, the pitch, and then the roll. Then things are very clear. What is the relation? You have the ready-made metric transformations. What is the application? Inertial frame of reference based stability equations. Aerodynamic stability equations transformed to inertial frame. This completes our last simple small subchapter of coordinate transformations and different frame of reference based stability analysis. This is what undergraduate students are expected to understand as a concepts. Thank you.